Hey, welcome to Functional Justin, episode 17. So in this video, I'm going to talk about the magic of lazy lists. And they say that any sufficiently advanced technology is indistinguishable from magic. And that's why I thought lazy lists were magic. When I first came across them messing around with Haskell, learning Haskell, I found that you can do things with lazy lists, like work with infinite lists. You can zip infinite lists together. It makes it possible to fuse multiple operations together, which you can't do in Scala with standard lists. So you can do something like map something, then filter it, and take a number of the elements, and the different operations are fused together. So you don't have to go all the way to the end of the list to map something, and then go all the way to the end of that new list and filter it. Lazy lists give you the ability to do things you can't do with ordinary lists. So in this video, what I'll do is I'll start by making a data type called a lazy thing. And a lazy thing will encapsulate the idea of lazy evaluation and memoization, which is once you understand how that simple data type is implemented, it's a small step to understanding how lazy lists work. And maybe that will take away some of the magic if you don't already know how they work. But I think it's interesting to learn about it, and whether or not you find yourself using lazy lists in your day-to-day code, I think understanding different evaluation models is really useful. Okay, so let's get started on building a lazy evaluating structure. I want to start by just building an intuition for the different kinds of evaluation that Scala has. So what we'll do is we'll make an expression that is just an integer. We'll call it a, and it's a Scala int. It's going to be an expression that prints a message. Let's just print evaluating. And after it's done that, we're going to separate that with a semicolon and then just return an integer, which is 10. So this is a good way to explore evaluation in Scala. So what happens is when I run this, you can see that it printed evaluating, and it also stored the result of this expression in A. So this is what we call eager evaluation. As soon as the expression is seen, it's evaluated and stored somewhere. So when we look at other types of evaluation, we're going to compare it to this one in terms of when it happened. So does it happen immediately or later on? And what happens to the result? Is it memoized or cached in some way? So you can say that in this way, what happened is we evaluated an expression and we stored it in A. So if I was to reference A again a couple of times, and then run that, you'll see that it just prints evaluating one time, because obviously it doesn't evaluate that expression more than once. It only evaluates it when it's doing the actual store into that variable. And the same would be true if we pass this to a function. So by default, Scala is what we call eager evaluating parameters. So, or it's also known as strict parameter evaluation. So when you enter the expression as a function argument, it will be evaluated. The function will see the evaluated expression. It's only going to see the 10. It's not going to see anything else. So let's switch things around a bit. There's a way that we can do a different evaluation model called always evaluation. So in this model, every time you reference A, it will actually evaluate again. And to simulate that, we could represent A as a function. So it's just a function returning int. And so we represent this as a function returning an int. And when I run this, obviously we don't reference A, so this function doesn't get called and it won't print evaluating. So let's just run it, and you can see there's no output. Now if I was to run it again, I'm going to reference A by invoking it like a function. So now you can see it's evaluating and the value is 10. And then if I want to do the same thing again, now you can see that it evaluates every time we access it. So not really anything surprising, but it's interesting to think of this as the different evaluation modes that you can emulate or achieve in Scala. So the next thing I want to think about is, we should mention the memoization of this. So obviously the value is not stored anywhere in this case. With always evaluation, you just always execute it when you want the value of the expression. So the next thing we're going to think about is lazy evaluation. So what I want to do is build a data type that we can use to store a lazy value and then only compute it when we want it. And then after we've computed it, we want to store it so that it's only evaluated once. And that's the essence of lazy evaluation. So we'll make a class and call it lazyThing. And it's going to be parameterized type, so we can make this with any kind of a. And then we're going to pass in a value a, just using normal syntax for now. Inside this class, what we'd like is a function that returns the value of a when the user wants it. So we would like the lazyThing to not calculate the value of a until the user asks for it. So the first thing we'll do is we'll store the value of a, and let's call it just value. And the type of that is a, and the initial value, value will be underscore, and underscore in Scala means give me the default value for this type, whatever it is. And that should be a variable, not a value, because this is going to change. We also want to store a boolean that tells us whether we evaluated a or not, so that we don't do it more than one time. So we'll make another variable, and we call it evaluated. And this is going to be a boolean, and it's going to be initialized with the value false. The next thing we want is a function that returns the value for the user, and this will be just value, and it's going to return an a. And what this will look like is a code block that is going to say, if I've been evaluated, then return the value. I'm going to have to give this a different name, so let's call it inner value or something. Everyone has their inner value. So if evaluated, then return the inner value, because we already know what it is. If it's not been evaluated, what we'd like to do instead is, first of all, we want to evaluate it. So inner val will be set to the value of a, and we will return, we will also set evaluated to true, and then we will return the inner value. So that's the essence of it, and it's not quite going to work yet, but let's print it out and, well, let's try it out and see what happens. So what we're going to do is create a lazyThing. We'll make a new lazyThing, and we'll pass in the expression from before. So that's going to say println evaluating, and then return the integer 10. So we're going to make a lazy value with the integer value 10. Missed parenthesis. I missed one and added one in the wrong place. There we go. So if we run this, we get evaluating, and then we returned something that we don't want. So what's going wrong? Well, the first thing is, what we got back here was actually a func, or a evaluated piece of code. In other words, the expression as an object. It's not what we wanted. What we wanted was to not evaluate this expression when it comes in here, and only evaluate it when we need it. So instead of passing in the actual value here, what we could do is pass in a function that returns an a, and then when we want to get the value, we have to actually invoke it, and this gives us the laziness that we want. And what that means is that now our expression is not the right type to pass to the function, but we can fix that just by making it a function like that. And now when I run it, you see that we get the same nonsense back. So inner value is equal to a invoked. So one thing we're not doing here is actually dereferencing our lazyThing to get the actual value. So all we're doing is printing a lazy thing up there. So now when I run it, you see that it's evaluating and we got a 10. Now let's grab that expression. As what I want to do is call it twice now. I'll just call it LZ1. And now what we want to do is to evaluate it twice, and we should see that it's only actually evaluated once. There we go. So we printed out 2 10s, but we only evaluated one time. So that's the beginning of our lazy data type. Now, if people who know Scala are probably screaming right now, because this isn't as good as it could be. There's some Scala built-ins that we can use, built-in constructs we can use to make this much better. So first of all, this idea of passing in a function that we can just call when we want is similar to a Scala concept called call by name. So we can use call by name. The syntax is very similar to passing in a function, and you just make it look like that. You've got this indicates that A is a parameter that's going to be called by name, which means that whenever we refer to A, we actually evaluate that expression again. The next thing we want is we don't need to invoke this like a function. We can just refer to it like a normal variable. So that looks neater. And now when we call lazy thing, we can pass in our expression directly. We don't need to store it in a function. I deleted too many braces. There we go. So we should find now that it evaluates once and prints twice. Okay, so still working. And we've simplified the code quite a bit. The next thing we can do is Scala has a built-in syntax for lazy values. So what we're doing here with the Boolean is remembering something is evaluated, then evaluating it. All of that work can be replaced by a lazy value. So we can get rid of all of that, and we can just say that we have a lazy val value that when initialized will be just set to A. So we can run this, and there you go. So lazy thing became a lot simpler just using a couple of Scala constructs that are ideal for this job. Okay, so lazy thing gives us the intuition for how to do lazy evaluation in Scala. And so now we just need to extend that to the collection type, and then we have our own lazy list, and then we can do magic things that I saw in Haskell. We can do them in Scala. So first of all, what we're creating is a data type, and then we're going to add functionality to it so that we can use it. So the data type is going to be represented as an interface, and in Scala the most usual way to represent some kind of interface is to use a trait. So we're going to create a sealed trait, which means that you can't extend it except for in this file, which is what we want. And I'm going to call it the LazyList, and it's going to be parameterized, so you can make a list of any type A, and it's going to have some functions that all lazy lists should share. So we're going to have the head is simply type A. We're going to have a tail, which is our lazy list of type A. I need a Boolean that tells you whether it's empty or not, so that will be just a Boolean. And that's pretty much all there is to the interface to our lazy list. And then what we'll do is we'll implement LazyList in terms of these two, in terms of this interface, by making concrete instantiations of our LazyList types. Now, before I go ahead and make the implementation of LazyList, I'm going to change the annotation here from just being A to being plus A. So what that means is that our LazyList is covariant in its parameter type, and that sounds horribly complicated, but it's quite simple. And I do intend to do a longer video about variance in the future. But for now, I can just sort of cover the basics of variance. So the idea is you have some supertype, let's say loan, and then you have a subtype of that, which might be a credit card. And by the rules of subtyping, what we can say is anywhere where you can use a loan, if you can use a credit card instead, because it has the same operations as loan, that means that credit card is a subtype of loan. This is called behavioral subtyping. So if it behaves the same as the parent in all the ways that matter, then it's a subtype. And this is also known as the Liskov substitution principle, from the also the L in solid, if you're familiar with that. But all of the jargon aside, this is how you define what something. This is how you define that something is a subtype of another thing. Now, what variance is it talks about subtype relationships with generic types or parameterized types. So what we're saying here is that we have a lazy list of type loan, and there's a subtype relationship between that and credit card. Or is there? So what that plus gives us is it says that I would like this type to be covariant in the parameter A. And covariant means just this, that if you have a lazy list of credit cards, you can use them wherever you're expecting a lazy list of loans. So you can substitute it just like you can substitute a credit card for a loan. And that's what covariant means. And that's not the default in Scala. And there are reasons for that I'm not going to go into right now, but there are reasons for that. And the default in Scala would be to not have any annotation there, and that makes this invariant. Now, invariant means that if you have a function, say, that takes a list of loans, it wouldn't take a list of credit cards. It's not the same thing. And another thing you can do is change this to contravariant with a minus sign. And what that does is flips the subtype relationship. So it means that wherever you want a credit card, you can substitute a loan as a subtype. So anyway, that's probably more than we need to know for this particular video. But I just wanted you to understand that our lazy list is going to be covariant in type A. And the reason for that is really about ergonomics. So people using the library will find it more convenient. But in fact, in the case of our lazy list, it's actually important to the design, as we'll see in a moment. So I'm going to make an object and call it our lazy list, and this is our companion object where we can put static functions that are useful for building lists and doing operations on lists and so on. Now, all lazy lists share the same empty type. We only need one kind of empty list. We don't need to make a new empty list for every different parameterized type of lazy list. So I'm just going to make empty a val, and I'm going to create a new our lazy list, and the type of this is nothing. And the reason for that is nothing is what you call a bottom type. It's the type, it's the subtype of everything, and you can't actually use it for anything useful, but you can use it where a subtype is expected. So that means that because our list is covariant, the end of the list can be an empty our lazy list of type nothing, and this is really only used as a marker. We're not going to use the nothingness inside it or anything like that. It's purely because we want to share the same empty list with everything. So to make this an our lazy list, we have to implement the traits. So what we want to do is define the head to literally be just an exception. So if someone tries to get the head of an our lazy list that has nothing in it, that's an exception. So we can say no such element exception, and a little message for the user: cannot get head of empty list of empty lazy list. And the next thing we might want to do is throw an exception when you get the tail. So that's throw new unsupported operation, maybe. I think that's what the standard library does. No supported operation. No tail of empty list. And finally, the Boolean value is empty can just be the value. And that is all we need to do to create empty lazy lists. Now, more interesting than empty lists is going to be when you want to construct actual lists. So what that looks like is it's going to be a function, we'll call it cons, to construct lazy lists. And cons takes 2 parameters. First of all, it needs the type parameter a, and then it needs the head. And the head is going to be called by name because we want people to be able to build lists without evaluating the head. And then we want the tail parameter. This is going to be called by name too. And the type is our lazy list. And this is of type A. So that's the function. And we would like it to return a new lazy list of type A. So what does the head look like? We define head as a lazy value, just like in lazy thing. So lazy val head, and all we do is assign it to head. So remember, head is called by name, and head is a lazy val. So that means 2 things. Head will only be initialized if somebody calls the head function, and at that point it will evaluate this expression, which hasn't necessarily been evaluated yet, and then it will memorize it and store it in the head variable. And we want to do exactly the same thing for the tail. This is going to be tail. And then the isEmpty value, of course, will be false. So perhaps surprisingly, that's all we need to do to build lazy lists. And obviously we need a lot more functionality before we can actually use them for something. But it's interesting that just in 9 lines of code, we've created enough to actually build a lazy list, and well, not much else. So let's say we're going to make a lazy list just for fun. And what we'll do is cons this lazy list with the number 1, and then the tail will be another lazy list, and then the tail of that can be the empty list. So you can see that we pretty much have enough. We have enough to build a lazy list. So if I run this, nothing will happen, but we will have built our first lazy list. So the next thing we're going to do is to do something useful. Let's create the map function. So what do we need to do to map a lazy list? Well, first of all, the map function will be part of the trait. So in here, what we want to do is define map as something which takes a parameter b and a function that maps a to b, and the result was going to be our lazy list of type b. So in case you don't know, last week I did a video about non-empty lists, and so quite often I'm going to say empty list or non-empty list, but I always mean lazy list in this episode. So if is empty, so that's the first step. If the list is empty, we just return the empty list. Otherwise, we're going to create a new empty list. So we use our LazyList constructor, and the head of this is going to be the result of applying a function to the head. Now remember, this is a call by name parameter in cons. So even though it looks like I'm calling a function here and evaluating the head, I'm actually not. I'm just saying here's an expression that if we ever do it, it will apply this function to the head, and if the head isn't evaluated yet, it will now evaluate the head. And then the tail of this is going to be recursively defined as mapping the tail of this thing with f. So if we were to map this with a function that prints hello, and then returns the value a, the value of this now is still integer. Oh, I guess it's any. It should be integer. So let's fix that. So this should be like this. There we go. So what we've got here is a lazy list that's constructed of 1 and 2, and then we map it, and at each stage we print hello. So the question is, what will this do if we evaluate it? If we take LZ1, take the head of it, what it should do is print hello, and it shouldn't evaluate the second element. In fact, we should probably change it as well, just to make this more interesting. So what we'll do is we'll add 10 to it. So what we should see is we'll get 11, and then when we evaluate the head of the tail, we should get 12. So let's try this out. We just run it. There you go. So evaluating the head prints hello 1, and you can see that LZ1, this lazy list, only the head was evaluated, and only when we asked it to be. We can evaluate the head again, and nothing will happen. Or rather, it will only evaluate once, and then we can evaluate the tail. So that would be LZ1, get the tail, and get the head of that, and it should print the second number. And there you go. So now we have a lazy list, and we can do things with it. So the map function was very straightforward. Another useful function is to be able to filter lists. Now it turns out that implementing filter is easier if you have a way to dropWhile first. So what that means is we can implement a function called dropWhile, which takes a condition, and it will return a new lazy list, and it will remove all of the elements at the start of the list that match some filter, and then it will return the filter of the rest of the list. Now that sounds crazy complicated the way I described it, so let's just implement it and you'll see what I mean. So dropWhile is a function. It takes a filter function. Let's say that it takes each element of the list and returns true if that element should be dropped. And then the result of this function is our lazy list of type A, because we're not changing the type of the underlying elements. So what we do is, as usual, check to see if it's empty, and if it is empty, we just return the empty list. Otherwise, we're going to do something more interesting. We have to actually evaluate the head. So we say if head, if it's true, then we want to drop it. So what we do then is just return the list without this element. We just return the tail of this and dropWhile and pass the function in to that one. Otherwise, this is if f had succeeded, or sorry, if f had failed, then this is an element that we want to keep, and what we want to do now is return the rest of the list. So returning the rest of the list just means return this. So that's quite handy, and what I want to do is also make a helper function so that we can create lists from, we can create lazy lists from sequences. So that will make it easy to test things. So what we want to do is add a constructor function or an apply function so that we can pass in a sequence of elements and create a lazy list that contains those elements. Now bear in mind that these elements will be, this sequence we pass in is already evaluated, so what we want to do is just create a lazy list that can be constructed from this list, and that will just give us a way to get lists into the system so that we can do lazy things with them. So first of all, if the sequence that we provided is empty, then we can simply return the lazy list empty. Otherwise, what we want to do is create an empty list, and the first element of the lazy list is the head of the sequence that we passed in. So remember that the way variable arguments work in Scala is this is essentially a sequence, and so we take the head of the sequence, that's the head of the lazy list, and then the tail of the lazy list should be the the tail of the arguments, and we have to do this tricky syntax, which means take the rest of the elements from the sequence and put them in this function as a variable argument list. So that's a bit messy, but it's what we need to do, unfortunately, to make this work. So now we can make a lazy list more easily. We can say this is going to be a lazy list of numbers from 1 to 5. And now we can test dropWhile. So what I'd like to do is say, let's drop the numbers while they're less than 3. And that should return us the list 3, 4, 5. So we just do dropWhile, and then this should be less than 3. And if I was to get the head of dropped, that should give us the 3. And also let's print it. I've got an error. Why have I got an error? Right, because we need to call apply recursively, not just pass in the tail like that. That's better. So now I can go ahead and run that. And there you go, it printed 3. So the nice thing about this is that we dropped elements, and that means we had to evaluate them and discard them. And then we got a new lazy list back. And as soon as we start using that lazy list, it's as if we started the lazy list at the point that we were not dropping. And we didn't touch any of the elements after the 3. Just something to point out about creating a lazy list with this constructor is that when this list arrives at the function, it's already an eagerly evaluated list. So we can't assume that the elements of this list are unevaluated. But instead we're creating a lazy list from it. And it still means that we don't have to evaluate the whole list when we use downstream operations. So we can map this, we can filter it, we can take elements, and those resulting elements will be coming from a lazy list. The next thing I want to implement is the filter function. So we want to be able to take a list and filter the elements. And now we can do easily because we have dropWhile to base it on. You can think of filter as being taking a lazy list and filtering all of the elements at the beginning of the list, or the prefix of the list, and all of the elements that fail the filter will be dropped, and then we return a lazy list. And we can be sure that the first element of the lazy list will either be an element that passes the filter or the end of a list because we've exhausted the lazy list. So let's implement filter. So filter is going to be on the trait, and it takes a function, a filter function, and returns a lazy list of type A, just like dropWhile. So the first thing I want to do is create a new lazy list that has the initial elements dropped. So we can call it dropped. And this will be the result of taking this list and calling dropWhile on it. And passing in a filter function, which is essentially taking the filter function the user passed in and negating it. So we'll just say not FA. Need an equal sign there. I need to learn to code. So that's the beginning of the implementation, and then the next thing we want to do is check to see if that new list is empty or not. So if dropped is empty, then we can return either a new empty list or we could return dropped. But in my case, I prefer to just return a new empty list. And in fact, since our implementation of empty list is a singleton object, really doesn't matter too much. And then if otherwise, it means that we do have elements to return. So we will turn a new lazy list, and we'll construct this. And the head of this is going to be the head of dropped. So in other words, the first element of dropped should be something that passed our filter. And then the remaining is we take the tail of dropped And of course we want to keep on filtering, so we pass in the filter again. And that's the implementation of filter. So a combination of dropWhile and then returning a new list, which consists of the head element, which will have been evaluated. We needed to evaluate it to see whether it passed the filter or not. And then it will return the rest of the list as a lazy filter. So we're not looking at any elements after the first one that passes the filter. So now we can change this test code. Let's just add a few more elements. And instead of filtering, let's just return all of the even numbers. So we'll filter and say that we want to take the modulo of 2 should be 0, and we'll print that out. And you can see that the head is 2, so that's essentially the first filtered value. And then if we return the, let's say, the head of the list and return the head, that's going to return the second element, should be 4. You see it is 4. So at this point it might be useful to implement something so that we can view our empty list. So there's two useful functions here. The first thing is we want to be able to take a number of elements so that we can just say, let's take the first element or the first n elements from the list. So that's something I'll implement next. So this is going to go in the trait object, and this is the take function. And this is similar to the other function. It's just going to be a simple recursive list construction. So we can say take, it takes a parameter of n, which is the number of elements that we would like to return, n, and this will return a lazy list of type A. And so the first thing we want to do is say if n is 0, or if this is an empty list, then we would like to return an empty list. Otherwise, what we want to do is return a new list constructed from the head of this one, and the remainder of the list will be the tail, and we want to take n-1 elements from that. So that's a simple recursive definition of take, and this will let us work with infinite lists. It's useful when working with really long lists or infinite lists to be able to take a set number of elements. Another thing we want to do is a forEach function. So forEach means for each element I want to do some kind of side effect. So forEach will let us print out the list, for example, which is going to be useful. So it doesn't take any parameters, and it returns a unit, and the implementation can be recursive. In fact, on some of our functions we're going to make them tail recursive. I'm going to need to import the tailrec annotation, and you can see that I can't make this tail recursive right now, but I'll be able to once I've implemented it. So the implementation of forEach is to first of all, if this is an empty list, we don't do anything, so we can just say if is not empty, then do the following. Oh, my bad, it does take a function because we want the user to be able to pass in a function that does something. So it takes a thing of type A and returns unit. Okay, so if the list is not empty, then we want to run the user's function on the head of the list. And remember, it's safe for us to access the head of the list because we've already checked if it's empty. And then we recursively call forEach on the tail, passing in the same function. And that should be all we need to implement forEach. Now, you can see that this is a tail recursive function. What that means is we can do the tail recursive optimization on it, which is really important for LazyList because otherwise you can get Stack Overflow because we're dealing with very long lists. In order to make it tail recursive, we need to fulfill certain conditions. So one of those conditions that we have met is that the recursive call is the final call in the recursion, and we've got that. The other thing is it needs to be final, And the reason for that is if somebody came along and overrode forEach, that would mess up the compiler. It wouldn't be able to make the tail recursive optimization and account for somebody coming along and overriding this function. So that is done. So let's go back to our little demo. And what we want to do now is take advantage of our take function and our forEach function so that we can print the first, let's say the first 3 even numbers from our example list. And so we no longer need to call print on our list, and we no longer need to store the result. There you go. Now we're printing the first 3 elements of the list. So now we have take, and now we have forEach. Let's see what's next. Next thing I want to implement is a couple of ergonomic functions that just make the API a bit nicer, or a bit more what Scala programmers are used to, or what they expect. So when you're constructing a list, you can use different syntax to the cons function, the construct function. You can say I want to make a list that looks like this. Let's say I want a list that consists of 1, and then we're going to have a tail, and that would construct a LazyList of type 1. You can see that doesn't work yet because we didn't implement it. If I was to change this to LazyList from the Scala library, this works. And so this is a convenient way for users to both create lists and also deconstruct lists using pattern matching. So we definitely want to implement this in the DUCT version. So let's implement this using Scala 3 feature extension methods or extension functions, which make this a little bit easier to do than it appears in the standard library. In the Scala standard library, you can see this is version 2.13.4, so quite an up-to-date version. You can see that the way it works is using this value class. So you have to create a new class called deferrer that takes charge of implementing the functionality of the constructor that we want to make. And so you need this, you need this class, you need this implicit definition, so that the Scala compiler is able to say, if I have a LazyList on the right hand side, and any value a that matches that LazyList type, I should be able to apply the constructor to it. And the other thing to be aware of here is that anything that ends with a colon in Scala is right associative. What that means is we want to apply the function to the thing on the right rather than the thing on the left, which is, if you think about it, that's what this that's how this operator works. The right hand side argument is a LazyList, and we're calling the add element function or prepend element function to that with this as a parameter. So that's why we use that particular construct. Now in Scala 3 we can just implement an extension method to do this, so we don't need to create that extra class. We can simply define an extension, and it's parameterized in type A, and it's going to take some head value which can be called by name, so it's not necessarily going to be evaluated. And then we can define the append function like this, and the append function takes a lazy or call by name tail. So in other words, we can construct lists on our LazyList tail, or it doesn't have to be a tail, but it can be an empty list. But we're not going to evaluate it because it's called by name. It's lazy. So laziness is maintained, which is what we're trying to achieve on most of the code we write for the LazyList. And this is simply going to leverage the constructor function. So this is just syntactic sugar for the user, and it takes the head and the tail as an argument. So now we can construct lists in this way. and that would be a perfectly valid list. And then we can go ahead and print it out with forEach. And there you go. So the other thing the other thing I wanted to do was to be able to pattern match with this. And pattern matching is a little bit curious how it works, but we can just copy it from the standard library effectively. So implementing pattern matching, the way that it's implemented in Scala is you can implement it on a companion object for the operator. So we create the object for the operator, and then we're going to write any unapply function, and this is what's called by the pattern matching logic. So you can use this in a match, and so on, and unapply will be called under the hood. And what unapply does is says, given some object, what were the parameters that I needed to construct it? And so it sort of deconstructs the object, and that's what we're going to write here. So it's parameterized in type A. The input would be an our LazyList of type A, and what it returns is a option, because this doesn't necessarily succeed. And the type of the option is going to be a tuple of the head of the list and the tail of the list, which is an our LazyList. So if you think about how pattern matching on lists work, you normally match on a head and a tail, and that's exactly what this is going to allow us to do. So first of all, we just do the is not empty check. So if not is empty, s is empty, then we want to return the some tuple of the head and the tail. So all we need to do is split it like that. Yale, tail, not Yale. And otherwise we're going to return none. So that in fact is everything we need to pattern match on a LazyList. So let's just test that out. So let's take L1 and match it. And we want to match on a head and a tail, and we'll just print the head. Otherwise, we'll just do nothing. I used the wrong symbol. There we go. So now we can run this, and you can see that it successfully pattern matched and extracted the one from the list. So I'm getting near the end of the video now. There's two things I want to cover before the end. One of them is implementing everything we need to do this example function that you'll find in the documentation for LazyList. This is an interesting example. It's a bit hard to understand, but what it does is creates a value called fibs, which is a recursive lazy definition of the Fibonacci sequence. So if you're not familiar with the Fibonacci sequence, it's you take a list of numbers and you add the previous two numbers together. So you'll start with 0, 1, you get 2, then you add 1 and 2, you get 3, then you add 3 and 2, you get 5, 5 and 3 is 8, and so on. And we can use a LazyList to generate an infinite Fibonacci sequence. And this is a very concise way of doing it, and it's recursive, and it relies on correct implementation of LazyList to do so. So it's a good test for our code. It's very hard to understand because it's the way the recursion works is this is a thing that sort of eats its own tail. So you can see the first two elements of the list are concrete values 0 and 1. It uses a big int so that it can be used for very large numbers, and then it zips. It recursively calls itself and zips that with itself again and the tail of that, and then ultimately it maps adding the two things together. So it's sort of like if you imagine a snake gradually eating its own tail. And you have to have two elements at the start, or else otherwise the tail's not long enough for the recursion to work. But as long as you have these two elements, you can generate the entire Fibonacci sequence. So anyway, let's look at what we need for this. We've already got the syntax, so that's going to be fine. We don't have zip, we do have tail, and we do have map. And we do have tail, take, and we do have forEach. So in order to make this work, we need to go ahead and implement zip. Okay, so zip is very similar to map. So let's copy map as a starting point. Change the name to zip. And zip takes another list as a parameter. And the other list can be a different type. So it's going to be parameterized in type B, just like map is. So the parameter, instead of being a function that map takes, is going to be another list. And the type of that is going to be our LazyList of type B. And what it returns is a LazyList of the tuple A and B. So remember that the idea of zip is to zip two lists together, just like the teeth of a zip on your clothing. So again, check if it's empty. And this time we're also interested if the other one is empty. If either of the lists runs out of elements, then that's the end of the zip. So in either case, if either sides of the zip has run out of elements, then we return the empty list. And then we just return a new constructed list where the head of the new list is just going to be a tuple of the head of this list and the head of the other list. And the tail, of course, is going to be recursively calling zip. So we're calling zip on the other one's tail. So that's all there is to zip. So now what we should be able to do is copy the code from the example and see if it works. So we just need to change the type to our LazyList and get rid of these comment markers. And this should print the first 5 numbers, but let's print the first 50 numbers, why not? Now I preferred forEach spelled like this, so that's probably that error. There we go. And there you go, the first 50 Fibonacci numbers. So that's a good sign that our code is solid. I mean, it's working for a complex example. The next and last thing I want to talk about is folding. So I will implement fold left off camera because it's not as interesting, but I'm going to implement the foldRight function because folding right with LazyLists is actually more interesting than folding right with eager lists, with normal lists, and we'll see why in the next section. Okay, so to save some time, I've already implemented fold left. Looks like this. And fold left is a way to take some kind of collection and iterate over it and recursively accumulate some value. And the user passes in a function that takes an accumulator and it takes each value. And there's a lot of things you can do with fold left. And you can see from the implementation that fold left is tail recursive. And that's important because it means that we're not going to run out of memory using fold left. So for example, we could take an infinite list. Let's say we had an infinite list of ones. And I'm going to call this our LazyList of long. And this is defined as LazyList that has 1 and then more ones. So it's just a infinite list of ones created like a LazyList. The next thing we want to do is fold over this and take a large number of them and calculate the sum using fold left, just to show that we don't have any stack overflow issues. So we take ones, and then I'm going to take a large number of ones, let's say 10 million, and add them all together using a fold left. And we start with a base value of 0. Then we take the accumulator and each one that we get. And each step we're just going to add 1 or we can add a to the accumulator. And then finally we're going to print this thing out so we can see what the value is. So now it's running. There you go. So that turned my CPU fan on. You can see it did a lot of work. It printed out 10 million, and we can guarantee that we didn't run out of memory or get a stack overflow. So that's fold left, and fold left, as I said, has the advantage of being tail recursive. Fold right does not have that advantage, as we'll see when I come to the implementation. Fold right does have another advantage though, in that fold right can be lazy in the argument of b. So you can see the definition here, that the base value of fold right, and this is the accumulating value, is called by name, and in the function that the user provides, it's also called by name. And this gives us a special power for fold right, that it can stop iterating at any point at once, whereas fold left has to consume the whole sequence. And if you look in the standard library, you'll actually see that fold left for LazyList does not have that signature. And there's some discussion online about this. Somebody has written this up, essentially that fold right does not work in the Scala standard library. These various examples don't work because it's not implemented with the second argument to be lazy. So we can go ahead and implement it lazy like it is in Scala Z's ephemeral stream. And then these examples that you can see on this page, which I'll put in the show notes, should work just fine. So let's go ahead and implement fold right. So the first thing is, as usual, check to see if the list is empty. And if it is empty, then we return z, which is the base value the user passed in. And note that we will be actually evaluating the value. So if you give it an empty list, it will evaluate the base accumulator. Otherwise, we have a choice whether it is going to evaluate it or not. So the next step is we want to call the function that the user passed in. So that's f, and the first parameter is the head, and the second parameter, and remember this is lazy, so we're going to provide it, but it might not be evaluated. We have a choice whether to evaluate it or not. So this is going to fold right on the tail, and then we pass in the same accumulator and the same function. And that's it. So it looks fairly similar to fold left, but it's dramatically different because it gives you, firstly, it doesn't have stack safety, and secondly, it does have the ability to early terminate, which means you can use it for different kind of workloads. So I went ahead and did some example code here. I'm just going to uncomment this. So this shows you the difference between folding left and folding right. So I have a list of fish here. You can see the order of the fish. It goes salmon, shark, tuna, to eel, and then I fold left and fold right. When I fold left, all I'm doing is printing each value as we see it in the iteration, and then adding it to the accumulator. And then the same with fold right. Each time we see something, we'll print it, and then at the end we'll print the accumulated list of all the fish that we saw. So I'm going to go ahead and run that. So what you can see is in the fold left case in the top right here, it printed out it encountered the elements in the order that you'd expect. So salmon, shark, tuna, same order of the input list. And the output list, the base value, which is barracuda, is first in the list, and then the rest of the elements follow in the order they were given. This second set of printouts, starting with eel, that's the output from fold right. So in fold right, the first thing we saw was eel, which was the last element of the list, and then we worked all the way down till we got to salmon. And the output list is the z value is first, and then the list itself reversed. So you can see the behavior of fold left and fold right is somewhat different, and we can use them for different things. So this is with non-LazyList, but in fact, if I comment this out and use our LazyList, then the output value would be exactly the same. Of course, they won't be exactly the same yet because I didn't implement fold right. So let's just comment that out. And there you go. So this is fold left, print all the fish in order. So let's uncomment this and sorry, I did implement foldRight, so we should be able to run that. And there you go. You can see it's the right output. Now, let's investigate the capability of short-circuiting. So what I'm doing is when I see each fish, I add it to an accumulator, and just dereferencing the accumulator, remember that this is a call by name value. So just dereferencing that causes the recursion to keep going. So if I don't mention the accumulator at all, then it won't accumulate. So we can demonstrate that early exit behavior by modifying this. So what we're going to do now is we're going to look at this list, and as soon as we see a tuner, we're going to just return what we had already and stop the iteration. So rather than referencing ACK, which as soon as you reference ACK, which is called by name, that triggers the recursion to continue. So if we don't touch ACK, then we'll be fine. So we can say if A equals tuner, then we just return an empty list. Or we could, if we want to include tuner, we could return a list with just tuner in it. The important thing is that we don't reference ACK. And then otherwise we're going to recurse as normal. So when we run this now, I guess Metals is having trouble. Okay, so I had to do a clean compile in Metals, and everything's working again. So let's do look at this foldRight again. So what I'm doing, just to remind myself, is that I want to fold this list and append all of the fish together. But if I see a tuner, I just want to return the tuner and nothing else. This is going to stop the recursion, and it's going to accumulate the other things that we accumulated already. So let's go ahead and run. So there you go. We saw salmon, shark, and tuner, and our result was tuner, shark, and salmon. And of interest, you can see that we never saw the base value. So by ending the recursion early, you don't get the Z or the base value passed in. Okay, that's the end of LazyList for now. Thanks for making it all the way to the video. If you didn't just skip here. Would really appreciate a subscription or a thumbs up or both. And looking forward to making the next video. Thanks a lot. Bye.